Okay, so let me start by thanking the organizers for the invitation for this wonderful conference, Shravan and Rama. So let me start. What I'm going to talk about is something very recent work which I've been doing with my PhD students Vikash and Rashmi on understanding energy spectrum and buoyancy driven 2D bubbly flows. And I'll tell you why I'm working in 2D bubbly flows, right? Because most of the times one thinks of 3D bubbly flows, but I'll tell you exactly the reason for this and what's at least the problem that, or small or big, I don't know, but that we are trying to understand. So this is the outline of the talk, and after a small intro, I'll do a bit detour onto 2D turbulence. And the reason for that is just to put students and those who don't know the field of 2D turbulence in perspective of what I'm going to talk about. And then I'm going to go over and look at Hale-Shaw flows, where there have been recent experiments where people have observed something like turbulence. And then there is a question whether this turbulence has anything to do with 2D turbulence that one typically talks about. And then, to understand then, first we will look at single bubble dynamics and then the dynamics of a bubbly swarm. So let's go ahead. And, as I said, bubbly flows are ubiquitous in nature. You could have a bubble reactor and, people have written reviews on it. There is a recent review which is also very interesting, which indicates that the gases which come out of the magma form bubbles, and the dynamics of these bubbles could control how explosive or how dramatic is the volcanic eruption. So again, another interesting place. And of course, one is interested in looks at bubble dynamics every day when one prepares tea at home. And of course, motivated by all these things, over the past few years, we have been looking at the dynamics of, either droplet emulsions or a turbulent Rayleigh-Bénard convection where you have a phase change. So that's about introduction, but let's go ahead and let's, as I promised, first look at a simple 2D turbulence picture, okay? And so what one is thinking of is, here is an experimental setup where you have a soap film which is driven by what is called as a Kolmogorov flow, okay? And then this is a typical snapshot of 2D turbulent flow, and these guys, I think, Srinivasan mentioned both Kreiknan and Batchelor in his talks over the past few days, along with Fjordtift and Leith and others in separate studies, figured out more or less that, if you inject energies at some intermediate scale, then there would be an inverse cascade of energy, which would be accompanied, or which appears because of a constant negative flux of energy and a corresponding forward entropy cascade. And one could show that, by dimensional arguments, that if you assume a constant flux of energy, then you expect similar to Kolmogorov k raised to minus 5/3 cascade, whereas if you assume a constant flux of entropy, then you expect a k raised to minus 3 spectrum. And indeed, this is what was observed in this beautiful simulations by Guido Boffetta and his group, where they systematically increased the grid resolution and observed the presence of dual cascade. And notice that in the inverse cascade, right, you have a constant energy flux, whereas if you have a forward cascade, you have a constant entropy flux, okay? And now why I'm emphasizing it? It's because that if I generate some velocity field, which has a behavior which looks turbulent, which shows a slope, which is 5/3 or minus 3, one might be tempted to think of it as a 2-dimensional or 3-dimensional turbulent flow. However, if you want to really understand whether that is the case or not, you should look at the fluxes. And only if you find some constancy of flux, you would be able to say that it's like hydrodynamic turbulence that we know of, okay? And now I'll come to why I said this. So here are the recent experiments done by the group of Boucher et al., which were looking at Hale-Shaw cells. What they do is they inject bubbles from bottom. The bubbles look very cylindrical, okay? And the Reynolds number that they achieve are between 650 to 1100. The bond number, which is, so I'll define all these things much more clearly as we go ahead. But the most important thing is that this system is extremely confined, all right? And this is the typical snapshot from the experiment, where you show the bubble positions and the typical velocity fields. And then what they did was, from this, they calculated the energy spectrum only for the liquid phase. So they choose lines where bubbles are not present, and they observed something which goes like k raised to minus 3. All right, and then so this vertical line corresponds to a bubble diameter, and they said that the minus 3 slopes is between the bubble diameter all the way goes up to 5 times bubble diameters. All right, and then there was so the question was why you are observing a k raised to minus 3 slope. And so they suggested that they are observing k raised to minus 3 slope for the same reason as it is observed in 3D bubbly turbulent flows, buoyancy-driven bubbly flows. And there's a theory, sort of theory, which was given by Riso and others, which claimed that the vortex bubble interaction should lead to a spectrum which is like k raised to minus 3. Now, there was lots of hand waving going in there. One just assumed that the spectrum is just form of multiple noise frequencies and which lead to this kind of a spectrum. However, there was no indication of whether it's, this is exactly like Stokesian dynamics, or you have some nonlinearity playing a crucial role or not. All right. So that's the thing which we started off with. The thing that our aim was that, okay, can we understand this k raised to minus 3 spectrum by doing numerical simulations? Because if you do numerical simulations, you can actually look at the energy budget and then try to get an idea of, what is balancing what. So to do numerical simulations, you have to realize, okay, how do I simulate Hale-Shaw, right? And that's very simple. Hale-Shaw dynamics for most purposes can be thought of as 2D flows. And here is the Navier-Stokes equation. There is only one small difference, that because you are looking at extremely confined flows, you have an additional wall friction term. This is linear in velocity. So this is exactly like Ekman drag, which is one used to looking at in 2D turbulence. And of course, because I'm thinking of a buoyancy-driven system, there is a gravity, right, which is rho times g, and then there is a surface tension contribution, which is put up here, and it's the standard thing which you again would find in Chandrasekhar's book of how does one treat surface tension. And the density is looked at in terms of some color function, let's say. So when phi is 0, you are in the gaseous phase, whereas when phi is 1, you are in the liquid phase. And how does this fraction phi evolves? It evolves according to just d phi by dt is 0, and we are looking that each phase by itself is incompressible. So you also have divergence of u is 0, right? Now, how do we in reality integrate it? Well, we use two different methods. One is a spectral method for Navier-Stokes, and we couple it with front tracking to evolve this. This is our in-house code. And we typically in this regime work within Boussinesq regime, where the density of liquid is very close to the density of gas, and that simplifies the system a lot, right? And the other thing that we do is use a second order finite difference code, which Rashmi has modified to take care of our needs in terms of parallelization and also using periodic boundary conditions. And the good thing with this code is that this can handle high density and high viscosity contrast. However, you have to be careful about grid resolution things. So we never use, one of the things in it is to use a artificial, the mesh refinement thing. We don't use that. We always use equi-space meshes for all our simulations. So it becomes a bit more expensive, but we realize that's necessary. All right, so if I do a Boussinesq approximation for this system, which are these equations, then what do I get? The equations, of course, becomes much more simplified. Yeah, W is the gap between the bond, right? If you do Boussinesq approximation, these equations become extremely simple, and they are therefore conducive for a spectral method. So you have the standard material derivative for velocity. Note that the viscosity, because we are assuming it to be also similar, has just reduced to a simple Laplacian term. The gravity is reduced to this. And then, of course, there is a surface tension, right? And what are the typical non-dimensional numbers that if you are doing experiments or simulations you would be looking at? Well, the typical velocity is square root of g times d. That's what you would expect, where d is the bubble diameter, okay? The Reynolds number is defined like this. as usual, UD by nu. Then there is bond number, which is the ratio of inertia to the surface tension forces. So you get rho u square by d by mu again. And then, of course, Atwood number. So when you are thinking of Boussinesq regime, you are really thinking of small Atwood numbers. When you are thinking of high density differences, you are thinking of large Atwood numbers. So if you are going to think of air-water kind of a system, your Atwood number would be very close to 0.99, something like that. Right, so let's go ahead. And let's first think about, how good are these Helešo equations when you compare them with experiments. So we did it, and also there was a very nice thesis by this guy Wang in TU Leuven, where they did both experiments and simulations for single bubble dynamics. And one observes that, the picture is clearly, you do see that the bubble is going up, and then there's a vortex shedding somewhat similar to von Karman vortices. And the same thing the VOF is also able to reproduce. But the most crucial thing is that if you go on changing the gap, the distance between the two plates, the wake, the vortex, how long does it go, that reduces. So if you have extremely confined bubble, all the vorticity gets dissipated very quickly. On the other hand, if you increase the thickness of this, or the width of the Helešo element, then you see that the vortices travel more downwards. So one of the things that you can, or one of the ways to think about it is that if you are comparing your simulations with experiments, either you do stuff where you put in this thing, or you can, to simplify your life or make your life easy, ignore this stuff, but then always remember that you would be observing things at much lower Reynolds number than what experiment. So if you are doing a simulation with, let's say, Reynolds 10, most probably the experiments would be required to do the same thing, or to get the same feature, you need to do experiment at, let's say, Reynolds 100. Okay, so that's one thing that you have to keep in mind. And for what I'm going to discuss, I'm going to very conveniently set this drag term to 0 just to make my life simple. So let's go ahead. What were the earlier studies done by this? And it so turns out that one of the first, and at least I find it very impressive, studies of this system was done way before the experiments were even conducted by the group of Grete Tryggvason, okay? And they looked at 2D bubbly turbulence, right, at high Atwood number, bond number close to 1, but the Reynolds number was very small. This was set up more or less exactly like the experiment. However, the Reynolds number was much smaller. Remember, the Reynolds number in the experiment was somewhat like 700, whereas in the simulations of Grete, the Reynolds number was around 5.6, all right? And what did they observe? They observed something like an inverse cascade, something like a forward cascade, and they weren't able to run their simulations for a very long time, and one can understand that this was a Herculean task, because in 96, to do one iteration of this system, it took them 33 seconds, right? So you remember, imagine if they had to do this thing and all go up to, 10 times more of this, it would require them 160 days of continuous computation on a machine, which, at some point you need to analyze the things also, right? So they just stopped at this unsteady state. Then the question was that, okay, can we repeat these? And can we see whether we get the inverse cascade, the forward cascade, and then we can look at the flux. And if we see these things working out very well, then maybe because, these simulations were done at 0 drag, then everything is fine, and then we can look at much more complicated stuff. So then we did, or rather Rashmi did these very interesting simulations, but in her simulation, she allowed for coalescence and breakup of the droplet. Of course, with the present day computing, you can do much longer. We did it 10 times longer. We do achieve a steady state of kinetic energy. You plot so the inset shows how long were the simulations of Grete, and it stopped somewhere around here, whereas, you can run longer and get to the steady state. Of course, one can compare the energy spectrum that one obtains from these simulations with what Grete was obtaining, and one does find that the two agree, right? Pretty well, I would say, except for the small scale dissipation, which I think we have much higher grid resolution, so we do much better, of course. Grete was, by the way, doing these things at, I think, 256 square grid resolution, so we are doing way better than him. But then the question is, so do we really have the two cascades present in our system? And well, one of the easiest way to look at it would be draw the compensated spectrum. Let's see what you get. So here is k raised to 5/3 ek. This is arrow indicates the droplet diameter. Well, maybe at largest scale there is something constant, right? So good. Maybe there is an inverse cascade here. Then you plot KQBK. You see, okay, something constant here. Maybe there is a forward cascade here. And then, we said, okay, looks good. Maybe we should look at now the energy flux. Boom. And this is what we got. Okay, so let me take you through it. So these are all the terms. I'm just looking at the transfer function and the corresponding term for pressure, viscosity, gravity, and the surface tension. And what we found was something interesting. For length or for wave numbers, large, or for the sizes, for length scales larger than the droplet size, the dominant balance is between the gravity and the pressure gradient term, which would typically indicate of a baroclinic torque in the system, right? So that's the dominant balance. If you look at the transfer thing here, it's more or less zero. Okay, in front of any of these other contribution, it's zero. Okay, so what it's indicating is that the so-called inverse cascade is not there in reality. And whatever spectrum you are getting, actually, if you just put a negative sign and put it over here, there is scale by scale balance. That's giving you something that looks like k raised to minus 3, right? It's all right, but maybe there is a forward cascade. So let's draw the same thing on log scale. That's what we did, okay? So now remember this. Here, the surface tension and viscosity were negative. So if I plot them in log scale, I have to take their absolute sign. And when it crosses 0, you would observe a blip in the signal. So this is surface tension negative. There's a blip, and then surface tension becomes, the contribution at that scale becomes positive. Same for the pressure term, right? The viscous term is here, and these the red squares are the contribution coming because of the gravity. See, what does it indicate? It indicates that at large scale, again, no energy transfer taking place. No, nonlinearity is not important, at least for these Reynolds numbers. And what is the dominant balance? It looks like that the viscosity is balancing, when the droplets would undulate and do various things, those things are completely balanced out by the viscosity, viscous dissipation, okay? Huh? There's no wall, this is periodic boundary condition, okay? So that's the dominant balance here, all right? So then we were completely stunned that, all right, whatever was shown, observed earlier, at least at low Reynolds number, it's not really a cascade. You see an energy spectrum because of perfect scale by scale balance of these forces. Now, I must confess, we haven't still figured out how to do even a hand waving theory to get these two slopes. However, it's clear that the balance, there is no nonlinearity involved, and the dominant balances just determine what spectrum is going to appear, okay? So now with this, we then decided, okay, this is getting very complicated because I have a baroque pressure term which is doing something. So let's do something in two parts. In the first part, let's look at low Atwood numbers, because in this regime, and let's ignore coalescence in the system. So I'm going to do something, there's going to be no coalescence. That's the advantage of front tracking method. And then let's work with the Boussinesq approximation. So I'm going to do small Atwood numbers. And then let's investigate energy budget with varying Reynolds number, small to large. And then ask ourselves that if I go to large enough Reynolds number, but still keep Atwood numbers small, can I have an inverse cascade appear in the system? And how are the balances? So these simulations were done by Vikash. And so these are the equations when you go to the Boussinesq regime. And one thing to note is that when you are at small Reynolds number, then the typical structures that are forming are much larger than a typical droplet size, whereas as you increase the Reynolds number, small scale structures start to appear in the system. And if you look at the movie, okay, so this is the typical flow. So you have large scale circulation getting set up when you are doing the things at small Reynolds number, all right? And if you look at the same thing at large Reynolds number, you have much more rigorous flow, droplets collide into each other, the surfaces oscillate. So it's a much more complicated system, and you have small scale structures also getting generated, right? So let's go ahead with that insight. And let's first ask ourselves, can I understand at least small scale, small Atwood number, small Reynolds number dynamics? So what we did was we did simulations at 2 bonds numbers, and then we got something which resembled k raised to minus 3 for scales which were larger than the droplet diameter. Then we said, okay, but we are at low Reynolds numbers, right? And small Atwood number. Maybe I can do a Stokesian simulation. And we did a Stokesian simulation, and voila, you got k raised to minus 3 putting up to it, right? So that's very impressive. And that if you have a swarm of bubbles in Hale-Shaw kind of a setup, and you are in pure Stokesian regime, you're getting a k raised to minus 3 spectrum, right? And this spectrum, again, has nothing to do with cascades, right? This spectrum is purely appearing because of dominant balances. In this case, of course, there is no pressure term, there is no baroclinic term. So the dominant balance is indeed between gravity and the viscosity, right? And there is small surface tension effect. Okay, then we said, okay, let's do the same thing at higher Reynolds number and see what happens, right? You do the same thing at higher Reynolds number, and what you find is this. You have something like k raised to minus 3 now at length scales which are smaller than the droplet size. It protrudes a bit, and there's something like k raised to minus 5/3 appears. And then we started to think that, okay, maybe we are still wrong. Maybe it's still just the dominant balance. Then what did we say? Did we do? Okay, by the way, the inset shows how good is the k raised to 5/3. I won't say it's fantastic, but there's a small range, okay? Now what we did was, again, looked at the energy balance, and here something very interesting starts to happen. Look, the viscous dissipation is small, so if we are looking at large scales, the energy that is injected by the gravity, right, is completely balanced by the surface tension contributions. Okay, there is a small viscous dissipation coming up. If you look at the energy flux, you do observe a negative energy flux appearing. We looked at the entropy flux, there is no entropy flux, by the way. Okay, and if you draw, then there is of course the question, how do you understand what's happening at the scales which are smaller than the droplet diameter, right? What you do is, oops, okay. So I think I have missed that slide, but if you plot these things on the log scale, what you would see clearly is that at large wave numbers, it's also apparent from here, the viscous dissipation is completely balanced by the energy injected because of the surface tension, okay? And there we have an argument where you can show that if you do a balance of this, you would indeed expect to get a k raised to minus 3 spectrum. So the story then is that for sizes, for length scales smaller than the bubble diameters, right, you're still thinking of a dominant balance which is giving you a k raised to minus 3 spectrum. However, for length scales which are larger than the bubbles at the sizes, right, there is, again, I'm not saying, look, remember the numbers on the y-axis here are pretty large. So the dominant balance is indeed still between surface tension and gravity. However, an inverse cascade or an inverse energy flux start to appear, which might be the reason of why we are observing something like a 5/3 in our energy spectrum. We really don't know how to, how to look at it even more carefully than this. Then we said, all right, this is the picture that we have. Remember, we already looked at what happens at low Reynolds number. There things were scale by scale budget was there. So then we first looked at, okay, let's look at large Atwood number, and now redo the simulation at large Reynolds number and see whether we have the same features. And we indeed observe that lots of small scale structures are appearing when you just crank up the Reynolds number, right? Then you say, all right, again, let's look at the energy budget. What do we get? So this is the slide that I had shown earlier, where indeed we observed at small Reynolds number that, there was a scale by scale balance of different contributions. So let's go to large Reynolds number. And in this case, we observe something extremely interesting. What do we observe? We see that when you are doing things at large Atwood number, now the minus 5/3 regime comes out much more cleanly. You do have a k raised to minus 3 also. So at large Reynolds number, the point is that irrespective of the Atwood numbers that you're looking at, you do see both the spectrums appearing, or both the spectral slopes appearing. You look at the energy flux, you do see a negative energy flux appearing now. However, note that unlike the front tracking simulation, where the droplets were not merging, in the volume of fluid thing, the droplet merge. So there is a size distribution of droplets, which means that these droplets are going to inject energies because I have a size distribution. So the vertical arrow indicates the average droplet diameter, and around that, the droplets are, or sorry, average bubble diameter, and around that, the bubbles are going to inject energy into the system. So we do see a much broader inverse energy or negative energy flux in the system. If you plot the other contributions, you again see, like in the like in the case of low Reynolds number, that the dominant balance is still between the baroclinic term and the gravity. There is a small contribution because of the surface tension, and as was true even at small Atwood number, the contribution because of the viscosity term is reduced at high Reynolds number. So the bottom line is that if you are doing high Reynolds, small Atwood, the dominant balance is going to be surface tension and energy injected because of buoyancy for length scales larger than the droplet size. On the other hand, if you're doing large Atwood numbers studies, then the dominant balance is going to be between the baroclinic term and the gravity. Of course, again, over here, if you look at scales which are which are smaller than the droplet diameter, we do again find that the dominant balance is between the viscosity and the surface tension term. So at length scales which are again smaller than the droplet diameter, the surface energy injected because of the surface tension undulations are damped out by the viscous contributions. So that's the picture there. So at this point, I'm in time, so I just stop and I say that what we have realized is that for low Reynolds number, low Atwood number, nonlinearity is not relevant. You do see spectral slopes, by the way, which looks like k raised to -3 and k raised to -5/3, but that's for a completely different reason. Nonlinearity does not play any role. For higher Reynolds number, on the other hand, for scales which are larger than droplet size, we do observe presence of a negative energy flux. However, we never observed any forward flux of entropy. In the forward direction, the dominant balance is indeed between viscosity and the surface tension contribution. So with that, I'll stop. Thank you.
Thank you, sir. We'll have questions.
Yes, Jeremy.
So I had a question concerning the way you're computing the spectrum. So I guess you're taking into account the full phases.
So you're right, but that doesn't matter for at least for the small Atwood numbers.
Okay, but could it be that you have some kind of discontinuities at the interface between bubbles and the fluid flow, which are explaining UK -3, which would be something like a discontinuity of the gradients?
Okay, I agree, but so at least when we looked at the flow field, especially at the low Reynolds numbers, the discontinuities in the gradient are not so apparent at all. If you look at the spectrum, we don't see a kink appearing, especially the Stokesian simulations. You don't see a large discontinuity. But I see your point, I'll look at it more carefully. I haven't looked at that so carefully. And it doesn't explain what's happening at the large scales and why it's still, goes ahead even when you do simulations at small Atwood numbers, where there are no density jumps for that matter.
So I have two.
Yes.
One is what we expect in 3D. The second is the breakpoint from 5/3 to 3 - 3. Is it close to the bubble size?
Yes, it is close, but then, it's difficult to say that in the volume of fluid thing where you allow for bubble breakup and coalescence, because then you have a size distribution. So then you have a band. Okay, 3D we are trying to do. So that's the next goal to do, because you see the point is that till now, whatever simulations have been done for bubbly turbulence, they have been more with walls and trying to look at, what is the flow profiles, where do the bubbles cluster. No one has looked at it in this way. So that's at least my aim to do.
No one, right? And we'll thank our speaker.